Good morning, everyone. Welcome to my presentation for KIB 3024 Medical Electronics. Today, I will be presenting my analysis on input common mode and differential low-pass filtering in an ECG front end. So this presentation was prepared by me, Li Zhongzhe, with matrix number 230051009. Now, let's start with a brief introduction. An ECG is a biomedical signal used to measure the electrical activity of the heart. As you might know, this biomedical signal is exceptionally weak, typically falling entirely within the millivolt range. Due to the ECG signal is so weak, it's extremely vulnerable and can be easily affected by environmental and physical noise. Let's looking at the raw ECG signal graph on the screen. You can see how heavily obscure the actual heart rhythm becomes unstable when it's subjected to interference. There are several major noise sources that can corrupt an ECG signal. Firstly, we can frequently encounter 50 Hz or 60 Hz power line interference from nearby electronics. Second, patient movement will cause drifting and motion artifacts between patient skin and electrodes. Thirdly, electrode contact noise can refer to a variation to skin electrode impedance that can affect the quality of biopotential signal captured by electrodes. This variation can be influenced by factors such as the type of electrode used, the frequency of the measurement, and also the skin condition of different patients. Finally, the electromagnetic interference will disrupt the signal through radiative, inductive, capacitive, as well as conductive coupling. So that's why filtering is so critical in an ECG system. The useful ECG signal naturally operates at low frequency, whereas the unwanted noise usually contain much higher frequency component. Therefore, by applying an appropriate filter, we can successfully reduce those unwanted signal before the signal reach the amplification stage. The core advantages of filtering include preventing signal distortion, significantly reducing interference, protecting the amplifier input, and improving the common mode rejection performance. So before we go through to the filter, let's break down the two main types of noise that we will filter it. Starting with common mode noise. Common mode noise is exactly the same noise appearing simultaneously on both input lines. There's a classic example which is 50 Hz interference picked up equally by both the positive and negative electrodes. Ideally, these kinds of noise should be entirely rejected by the ECG front end. So in our circuit, grounded capacitor pairs will help to effectively reduce this noise. Next, we have differential noise. This is a noise that appears differently on the two input lines. The real-world factors like the skin contact quality, electrode quality, wire path, and environmental interface are never perfectly identical before two electrodes, which ultimately creates an unwanted voltage difference between two electrodes. Therefore, an internal capacitor will help us to suppress this by heavily reducing the high frequency differences between the two inputs. Why is it necessary to implement both common mode and differential filtering? Common mode filtering removes the shear noise, while differential filtering specifically removes the noise that exists between the two inputs. The ECG circuits will require both mechanisms simply because the real biological signals and real-world noise are not perfectly symmetrical. Therefore, by using this combination, it can give us far better noise rejection and a much more stable input balance. After introduce the type of noise, let's proceed to the filter circuit. Here is the filter that I've chosen in the ECG system. For this system, I've chosen a passive and low-pass filter network. This filter is deployed right at the front end of the ECG system. Besides, there are no active components used within the filtering stage itself. Its entire role is to carefully improve the quality of raw ECG signal before it's allowed to enter the instrumentation amplifier. Looking closer at the main component, the circuit executes three distinct filtering functions. Firstly, we have a low-pass filter path to the ground, and secondly, there is a differential amplifier that plays across two inputs. Thirdly, there is a second low-pass filter path to the ground before the signal passes through the instrumentation amplifier. Three parts work in unison to clear the input ECG signal. But why do we use multiple filters? It's because the real ECG inputs are never perfectly identical, and the noise can actually convert from common mode to differential mode. Therefore, a single filter simply cannot remove all types of noise effectively. The different capacitors target different noise mechanisms, and utilizing multiple stages maintains input symmetry while protecting the common mode rejection ratio. This approach is significantly improved robustness under non-ideal conditions. Ultimately, this allowed the ECG system to work reliably on real patients with unequal electrode contact. inside noisy environment facing EMI, and within the variable devices subject to the movement. Let's examine the function of the first low-pass filter pair, designed as LPF1. This is the very first pair of capacitor and resistor located on both input lines. It works to filter each input line separately, shunting high-frequency noise directly to ground, while actively reduce common mode interference. This stage is important because it keeps both input paths completely balanced. It prevents one input from being filtered differently than another one, which heavily helps to preserve the CMRR. Moving inward, we have the function of second pair of low-pass filter, or LPF2. This is the second consecutive pair of similar capacitors and resistor. It provides necessary additional filtering to further improve noise suppression. This maintains signal symmetry over a much wider frequency range. It's crucial needed because the real ECG circuit are not ideal. Factors like electrode impedance and trace parasite are rarely perfectly matched. So adding a second stage vastly improves the circuit practical performance. In the center of the network, we found the differential capacitor. This capacitor is connected straight between two inputs. It filters differential noise by allowing the low frequency ECG signal to pass through isolated, while aggressively equalizing the input at high frequency. This physically reduces the high frequency voltage difference bridging the two input lines. And why is this component different from the others? Well, the other capacitor primarily move common mode noise to ground. The differential capacitor works directly between the signal line. It targets the differential signal exclusively, not the ground reference noise. To summarize the working principle, the low frequency ECG signal will pass through this entire network with minimal attenuation, while the high frequency noise is severely attenuated by the RC low pass behavior. Concurrently, the common mode noise is reduced by the matched capacitors route to the ground, and the differential high frequency noise is squashed by the differential capacitor position between the inputs. As a result, the instrumentation amplifier is guaranteed to receive a clean and balanced signal. Here is the circuit simulation by using a Tinati software, which the parameter is already altered for us to achieve the signal filtering. Let's move into the mathematical circuit analysis. So firstly, we calculate the resistance per leg. There are two legs in this circuit, which is the top and the bottom leg. So the formula of this is only by adding all the resistance together. So we'll see that the answer will become 229.8 k ohms. After calculate the top leg resistance value, we calculate the bottom leg and add the values together, and we can see that the answer will be 495.6 k ohms. Okay, after we calculate the equivalent resistance, so now we are going to calculate the equivalent capacitance. So we can see that for the capacitor that line in series, the equivalent capacitance would be the original capacitance divided by 2, and but now we are skipping for this step because it's fundamental knowledge. So after that we can see that the equivalent capacitance for this capacitor network would be 2.42 nanofarad. Okay, by using the total parameters that we obtained, we can now calculate the cutoff frequency for this circuit. So here's a formula provided, and by substituting the value that we obtained, we can finally get the cutoff frequency of 143.09 Hz. Looking at our broadboard simulation from Tinati, we have successfully verified this calculation. The simulation shows that our desired cutoff frequency is sitting accurately at 143.62 Hz with attenuation of negative at 0.97 dB, which is very near with negative 9 dB. And why our cutoff frequency is negative 9 dB is due to our maximum dB is actually negative 6 from our circuit, so that negative 9 is only less by 3 dB from negative 6. And this slide showcases a time series circuit simulation. The graph visualizes the output, specifically VF1 and VF2, against the input raw signal VG1. You can clearly see that how the erratic spiky noise present in the raw input is moved out into a clean and this variable wave in the filter output. To conclude, let's discuss the biomedical relevance of this design. This specific filter network is exceptionally suitable for ECG application because it contains several criterion features. So firstly, it's tailored strictly from 0.05 Hz to 150 Hz which is the diagnostic range required for clinical ECG readings. And secondly, it effectively safeguards sensitive biopotential ranging from microvolts to millivolts against the high-frequency physiological artifacts. And thirdly, by suppressing the noise prior to the gain stage, it can prevent amplifier saturation and signal clipping. And fourthly, it drastically minimizes the signal-to-noise ratio. And finally, by minimizing a high-frequency common mode noise, it ensures that the instrumentation amplifier will always operate safely within its linear region. Thank you for your time and attention.